Hello and welcome to this talk about system engineering. I will speak about integrated MBSE methodology case study. I am Etienne Juliot. I work for Obeo company, which is a company which creates software for modeling whatever is your domain. And we do this with also a focus on MBSE in partnership with Siemens. I will start by explaining what is model-based system engineering. It is an approach which is cross-domain. It's work for energy, transportations, defense, other. And for this talk, I will focus on the automotive domain. When you want to design a new future, you have to discuss with your customer about the different aspects you want to improve. Then you need to capture the requirement and to design your systems with subsystem, subcomponent to manage the complexity of your design. When you finish to have an architecture, you have the input to the different stakeholders which are focused on one aspect, software, electricity, and others. But currently, there is a very big problem is the integration issue because you have too much specification which are not structured enough. By using model-based system engineering, you help all the stakeholders to have better and more precise specification of your architectures, and you avoid integrations issues. Oops. The main objectives of model-based system engineering is so better understand the customer need and have a way to be focused on the need. Then you can define the solutions, not alone, but in a collaborative way with different stakeholders. You can also secure the architecture in terms of software, hardware, engineering by being sure that you are consistent. And you prepare subcontracting by defining clean scope. You can do early validations of architecture choice, and the earlier you do the choice, the more efficient you will be in your process. You can also prepare and master the validation and verification, as you have precise architectures and functional descriptions. It's help to do the test. But doing this alone, in a standalone mode, is not enough. You need also to do this in an integration way. To do this, we have three pillars. The two first one are the methodological guidance, named Arcadia, Capella as a technology, which is an open source technology created by an open source community led by Thales. And these two new evolutions of the system engineering approach are integrated inside system modeling Workbench, which help you to stay integrated and start integrated and stay integrated. The trend about this approach and Capella project is very, very good, as you can see. There are more than 300 organizations which publicly say that they adopt Capella. As you can see, the lines grow up very quickly, so we are on a vibrant community trend. So now let's focus on the case study and go more in the concrete example. This example will be about a rain detector in my car and a system to do my car going slow down or to suggest a speed, depending on the rain. To do this, I have a methodological guidance. There are several activities, but where I would like to focus is the split between the need and the solutions. In this way, you don't pollute your design and your capture of the need with internal problems, internal concerns. You are completely focused on the discussions with your customer. And when you are doing the solutions, you have a full traceability how your needs has been translated to concrete solutions. So you have a guidance. Let's go in this step-by-step process. First, I will create the operational analysis. So I will focus on how the user interact between them and what they need to accomplish. When I open the Workbench, I have the methodological guidance, which is directly inside the tool, as you can see. So I see all the different steps, and I can open an operational context diagrams. I will create a new operational entity, which will be the weather. The weather has an activity which is raining. At this step, I didn't describe the system itself. I really want to describe the environment. And the rain will have interactions with the vehicle, not just my system, but all the overall vehicle, which is rain running, to provide status, and I can do a trade-off and to precise the requirement with my customer to say, okay, let's just focus on the recommended speed we will see later for an autonomous vehicle. I can also highlight some process on the same diagrams to show a kind of scenario. This will be very useful later when I will need to provide constraint on this process about safety, about cost and other, and when I want to apply testing scenarios. Of course, there are plenty of other diagrams like sequence diagrams, capability, missions, descriptions. Then I will describe my system, but I will describe my system as a black box. I want to focus on the integrations with the external. I don't want to go much in the detail of the internal, not at all. So I will translate automatically, thanks to accelerators, my operational descriptions to a system vocabulary. This time I will speak about component, I will speak about functions. But of course, thanks to the transitions, you have traceability link between the two steps. So I still have my weather. Of course, inside my weather, I can allocate the functions rain, so that's basically the same than before. But this time, I will go much in the details to describe that I need an external entity, an external actor to detect the rain. It will be my rain sensor, and I consider it's outside of my responsibility. I will create a function inside this rain sensor because it needs to perform a detection of rain. For my own system, I will create a new function too to adapt the speed to the weather condition. And then I will configure the functional flow, the functional exchange between these functions to make it consistent. As you can see, it's very easy to read. When it's green, it's about function. When it's blue, it's about component architectures. And I can go to my customer and say, do you agree with this? And he can say, no. The rain sensor has to be part of your responsibility. You can increase your code about this, but you have to take care about this. First kind of trade-off. So I drag and drop these functions under my responsibility, and I can remove the external actor. And in this way, you define a contract interface with the relevant external world of your system. Again, you have plenty of other diagrams. All of them are synchronized, like the state machines and others. When you finish to discuss with your customer, you start to define the internal of your system. So you open the box. And by doing this, you can do breakdown diagrams to describe different subcomponents. You can also describe the same component in architecture diagrams, like a regulation adapter. And you can define, allocate functions to more precise components. By doing this, you start to define a clear scope of responsibility to your teams or to your suppliers. And as you can see, I define new functions this time, which was not part of the initial specifications, to choose how I want to display the speed advice. Last step, it's about physical architectures. I define the contract, how I want to implement a physical part of my system. Is it with this kind of CPU or is it free? Or for example, does the bus have to be a hardware or a pure software approach? And you don't go too much into the details, that's just the contract. You have a full traceability across all these different activities, and it is linked with requirements. The feedback of this is by having this methodological guidance, it's really helped to ramp up and to make a large amount of different stakeholders which are able to author by themselves this kind of system architectures diagrams. Lots of users already adopt this, and they are cross-domain again all over the world. Now let's go to the integrated part of MBSE. In terms of integrations, the end game is to enable digital thread, which means that I want to have a continuity between these architectures to the downstream engineering, electrical, electricity, software, simulations. So by having this continuity, if you have any modifications, you master the impact, and you can do closed loop modification in a more agile way. Our partnership between Obeo and Siemens to define the different future parameters and other. On the right part, you have the product validation, and in the middle, all the connected engineering. And everything is fluent between these different steps. So we created System Modeling Workbench to do this. The first feature of integrations is about enabling the storage and the management of the project and the lifecycle of the project inside Teamcenter. Then you have direct access to your data inside Active Workspace. You have also the RFLP federations to fill the gap between a fine-grained architecture design and the BOM. And you have also the requirement integrations, so you can just easily drag and drop requirement to an element inside the workbench, and you have the traceability which is enabled. It's really helped to collaborate and to enable what I call the integrated model-based system engineering. On the Teamcenter aspect, you have now the ability with the SMW 5.0 to have a federation of your data to the different existing element data you manage inside Teamcenter, which is very useful to keep data in sync and to be sure that you benefit of the authoring approach and guidance of System Modeling Workbench, and you can have all the connectivity with other tools which are already connected with the BOM. Let's have a live demo of this. You can see that I can select some functions which need to be promoted as coarse-grained data. Then I will export this to Teamcenter. They will have a translation actions between my functions inside the workbench to the BOM, and you can now directly navigate and browse this element directly in the web inside the Active Workspace. You benefits of feature like the capability to see impact, traceability, dependency between different data. You can also modify some small elements, small information like the name, the descriptions, and you can do this directly in Active Workspace, and we can resynchronize. The goal is not to design all your system in Active Workspace. It's not at all the way we propose to do, but it's really convenient to be sure that you can easily collaborate with persons which are on the Active Workspace side. For the requirement, here is a live demo. You just drag and drop directly your element in your Workbench, and boom, you have the traceability which is in place. And when if you do a modification on your requirement, you can refresh, manage the life cycle and the conflict. And when you push back your traceability, even if you made traceability link between requirement to a fine-grained Capella element, the traceability will be promoted with the Teamcenter object. We have also Teamcenter parameter support, so you can also drag and drop parameters directly on your Workbench, and you can render them graphically inside your diagrams and use them in your definitions. We also enable import-export between SysML to enable interoperability with a focus on IBD and BDD. And something very important is how we scale in a large project, how we manage to have a large team which are focused on different aspects of your systems. So to do this, we propose system to subsystem transitions. So you extract a subcomponent at your logical design as a new system model, a new file, which could have its own lifecycle, and which could be managed directly inside your team with Teamcenter, but also to a supplier, for example, which need to work in a standalone mode. We support reuse. Thanks to building blocks definition, you can store in libraries in Teamcenter, and so you have some record, and you reuse some record in your replica inside some project. So you have a good reuse while we keep synchronization. You can also have a second kind of collaborations, which is inside your team of system engineering. It's the same experience like with Google Drive, Google Docs, or Office, where you design in live with other stakeholders to your current versions of your models. And when you finish to work on this, you can publish them to Teamcenter for stable versions or to promote to other teams. So to do this, we have a product called Team for Capella, which is an add-on to SMW, and it's very, very easy to understand. You are a user, you modified, in this use case you have Bob on the left side, which modify, as soon as you modify, you have a lock at the fine-grained level. So another user cannot do any conflict, but he can continue to work on other part of your domain. And as soon as somebody is saving his model, the lock are released, and the models, the diagrams are refreshed automatically. In a nutshell, what we propose in this way is a guidance, a complexity management and productivity tools, the capability to do trade-off analysis, and a good extensibility to manage your specifics, the digital thread with Teamcenter in the loop, the replicable element and library to do the reuse, some automated system to subsystem transition to scale. It's very easy to ramp up, it's modern, and it's future ready. For example, we are working on SysML v2, we are working to cloud support and other specific domains and future for having an exciting new versions in the future. All of them provide you not only a language, but a full experience of system engineering to start your project in an integration way, but also to stay for all the life cycle of your project integrated with all the other domains. Thank you, and use the chat if you have some questions. Thank you.